So let's take a look at the first series test, the test for divergence. So let's say we have the series from n equals 1 to infinity of a sub n. Now if we set the limit of a sub n, so we say the limit as n approaches infinity of a sub n, and that does not equal 0, then we know the series from n equals 1 to infinity of a sub n will diverge. And so keep in mind, this is only a test for divergence, not a test for convergence. So obviously if the limit does not equal 0, then it diverges. But if, let's say, we get the limit as n approaches infinity of a sub n equals 0, we cannot say much other than the best we can say is that it may or may not be convergent. Or we have to use another test to figure out whether it actually does or does not converge. So for number 1, let's say we have the series from n equals 1 to infinity of n over n plus 5. Now if we were to use the divergence test on this series, then we can just set the limit, so the limit as n approaches infinity of a sub n, or a sequence which is n over n plus 5. So this is basically a problem of n behavior. So notice how we're looking at the highest degree of the top and the bottom. So the highest degrees are n to the first and n to the first. And if they are the same power on the numerator and denominator, we're just going to look at their coefficients. And their coefficients are 1 and 1. So the limit is going to be equal to 1 over 1 or 1. Now remember that the limit as n approaches infinity of a sub n, if that does not equal 0, then the series will diverge. And our limit is 1, which is not equal to 0, so then this series will diverge by the divergence test, and I'll just label it as dt. And remember, it is important to label what test you use to come up with your certain conclusion. So in this case, we just wrote a diverges by dt. So for number 2, let's say now we have the series from 1 to infinity of arctangent of n. So once again, to use the divergence test, we're just going to use limit notation. So the limit as n approaches infinity of arctangent of n and so if you plug in or infinity for n, we'll get arctangent of infinity. And if we were to quickly draw the graph of arctangent of infinity, it will look something like this. And as that x value gets bigger and bigger to infinity, it reaches a horizontal asymptote, and that horizontal asymptote is at y equals pi over 2. So the limit as n approaches infinity of arctangent of n is going to be equal to pi over 2. Notice how pi over 2 is not equal to 0, so this series will diverge by the divergence test. So now for number 3, we have the series from n equals 2 to infinity of 2 over n squared minus 1. So once again, using the test for divergence, we'll set up limit notation. So the limit as n approaches infinity of 2 over n squared minus 1. Notice how this fraction is bottom heavy, meaning we have n squared, or the highest degree, in the denominator. And whenever the fraction is bottom heavy and we're looking at n behavior, as the limit goes to infinity, this series or this limit will go to 0. And notice how 0 will be equal to 0, so we cannot say it diverges. And at the same time, this series is only a test for divergence, not for convergence. So the best we can say is that we can use another test, or it may or may not converge by the divergence test. Now what you'll actually be able to do with this fraction here is use partial fraction decomposition, and it'll turn into a telescoping series, and that is a test you can use to find out the actual converging value. So now we have the series from 1 to infinity of the nth root of 2. So once again, using the divergence test, we set the limit as n approaches infinity of the nth root of 2. So this may be a little bit difficult to conceptualize, but if you think about it, no matter how big the root is, the square root of 2 will never, or the square root or the cube root, or maybe even the 100th root of 2 will never equal 0, but it'll probably get closer and closer to 1. So let's just say the limit is about 1, and that is not equal to 0, and because it's not equal to 0, this series, the nth root of 2, will diverge by the divergence test. So let's take a look at the p-series test. Now the p-series test is very similar to the p-test for integrals because all we're looking for is the exponent. So if we have this series from n equals 1 to infinity of 1 over n to the p power, if p is less than or equal to 1, then the series will diverge. And if p is greater than 1, then the series will converge. So since this is a pretty simple test, we'll just be going over a couple of quick problems. So for number 1, we have the series from 1 to infinity of 1 over n to the 9th. Obviously our p value, or the exponent value in the denominator, is 9, and 9 is greater than 1, which means that the series will converge by the p-test. For number 2, we have the series from 1 to infinity of 1 over the square root of n. Now obviously I have to change the square root of n and sort of put it in the form where we have an exponent. So I change it to 1 over n to the 1/2. So that is going to be our p value. So if p is equal to 1/2, 1/2 is less than or equal to 1, which means this series will diverge by the p-test, or pt. For number 3, we have the series of 1 over n. If our p value is just 1, because since we're taking n to the first power, that is less than or equal to 1, so it will diverge, obviously, by the p-test. And this is also a special type of series here. The series of 1 over n is called the divergent harmonic series. So whenever you see the exact series of 1 over n from 1 to infinity, you know it will diverge. And finally, for number 4, we have the series from 1 to infinity of 1 over the 5th root of 1 over n to the negative 1st. Now obviously this is just a matter of simplification, so I'll rewrite 1 over n as n to the negative 1st. So we have the 5th root of n to the negative 1st to the negative 1st power. Whenever you have a power to a power, you can multiply the powers. So you have 1 over the 5th root of n to the 1st. So then 1 over the 5th root of n. And so I can rewrite the series as 1 over n to the 1/5 power. Since our p value is equal to 1 over 5, and that is less than or equal to 1, then this specific series will diverge by the p-test. So let's take a look at the geometric series test. Now keep in mind that there are only 2 tests where you can actually find the legitimate sum of the series, and those are the geometric series and the telescoping series, which I'll cover in a later video. So getting started with the formula here, if we have the series, let's say, from n equals 1 to infinity of a, which is just a constant like 2, 4, or 1/3, times r, and that value is taken to the exponent n minus 1 power. If the absolute value of r is less than 1, then the series will converge. And if the absolute value of r is greater than or equal to 1, then the series will diverge. And if that series does converge, it will converge to the value of a sub 1 over 1 minus r. And keep in mind that a sub 1 is just your first term when you plug in 1 for n. And also keep in mind that the geometric series, it doesn't have to be in the form of r to the n minus 1. It can also be in the form of a times r to the n power. Or it doesn't even need to have an a. A can just be 1, and you can just have r to the n power. But all three of these ways you can still use a geometric series test. So for number 1, let's say we have the series from 1 to infinity of 5 times 2/3 to the n minus 1 power. Now notice how this is exactly like in the form of the geometric series test, where we have our a value and our r value taken to the n minus 1 power. So in this case our a is going to be equal to 5, and our r is going to be 2/3. So once again, if the absolute value of r is less than 1, then the series will converge. And if the absolute value of r is greater than or equal to 1, then the series will diverge. Since our r is 2/3, the absolute value of 2/3 is obviously equal to 2/3, and that is less than the value of 1, so our series will converge by the GST, or the geometric series test. And to find what exactly the value is that it will converge to, once again it's just a sub 1 over 1 minus r. So in order to evaluate that a sub 1, I'll just plug in 1 for n. So a sub 1 is going to be equal to 5 times 2/3 to the 1 minus 1, or to the 0 power. Anything to the 0 is 1, so 5 times 1 is going to equal to 5. So we'll get 5 over 1 minus r, and our r value is equal to 2/3. So 5 over 1 minus 2/3. 1 minus 2/3 is obviously 1/3. So 5 over 1/3 is equal to, when I divide by 1/3, I multiply by the reciprocal. So 5 times 3. And the series will converge to the value of 15. So now for number 2, let's say we have the series from n equals 0 to infinity of 1 over the square root of 2 to the n power. Now this might not look like the geometric series test at first, but what I can do is manipulate this series. So I can actually change 1 over the square root of 2 to the n power and bring it outside of the fraction. So I can rewrite this as 1 over the square root of 2, the entire thing to the n power. Because remember, when you take a fraction to the n power, you have to multiply, or you have to take both the numerator and the denominator to the n power and distribute that exponent. So if we distribute, we'll get 1 to the n over the square root of 2 to the n. And no matter what you plug in for n, 1 to the n is always going to be just 1. So I can remove that n, and we'll get back to where we started. So if I rewrite it as the series from n equals 0 to infinity as 1 over the square root of 2 all to the n power, now it looks more like a geometric series. Obviously we don't have the a value, but we don't need the a value, so it's just 1. And the r value is what we need here. So since 1 over the square root of 2 is our r, being taken to the exponent n. And remember, it doesn't need to be n minus 1, it can also be in the form of n. And so the absolute value of r, or the absolute value of the 1 over the square root of 2, is still equal to 1 over the square root of 2. And that obviously is less than 1, which means this series will converge by the GST. And to find what exact value it will converge to, once again, we just take a sub 1 over 1 minus r. A sub 1, I can just plug in 1 to the series. So that will equal to 1 over the square root of 2 to the first, which is obviously still 1 over the square root of 2. So once again, using this formula, we'll have 1 over the square root of 2 divided by 1 minus 1 over the square root of 2. If I find common denominators in the denominator, I can just rewrite 1 as the square root of 2 over the square root of 2. So then we'll get 1 over the square root of 2 over square root of 2 over square root of 2 minus 1 over the square root of 2. So then to simplify, we'll get the square root of 2 minus 1 over the square root of 2. And dividing by this fraction means multiplying by the reciprocal. So I'll multiply by the square root of 2 over the square root of 2 minus 1. And then the square root of 2's will cancel. So we'll get 1 over the square root of 2 minus 1. And that is the exact value which the series will converge to. So now for number 3, we have the series from 1 to infinity of negative 3 to the n minus 1 power over 4 to the n. Now, similar to the previous problem, this doesn't look like a geometric series at first, but we have to manipulate this series in a way so that it looks like the geometric test. So notice how in the exponent we have n minus 1. So using properties of exponents, obviously we know that when you divide by exponents, you will subtract them. So I can rewrite negative 3 to the n minus 1 as a negative 3 to the n over negative 3 to the first. Because once again, when you divide, you subtract the exponents, and when they have the same base. Over 4 to the n. So I can rewrite negative 3 to the first as just negative 3. And then when I divide by 4 over n, it's the same thing as multiplying by 1 over 4 to the n, or the reciprocal. So when I simplify it, I'll get negative 3 to the n over negative 3 times 4 to the n. Now I actually separate this into two fractions and bring the negative 3 outside. So if I were to rewrite this, we'll get negative 3 to the n over 4 to the n times negative 1/3. Now, similar to the last problem where we could factor out similar exponents, we can do the same here. So if I were to rewrite negative 3 to the n over 4 to the n, I can rewrite it as negative 3 over 4 all to the n power times a negative 1/3. So now if I were to rewrite the series, we have the series from n equals 1 to infinity. This will actually be the a value because it's a constant, so I'll put it up front, times negative 3/4 our r value taken to the n power. So now it looks like a GST test, since this is our a value and negative 3/4 is our r. The absolute value of r is going to be equal to the absolute value of negative 3/4, which is 3/4, and 3/4 is obviously less than 1. Now this tells us that our series will converge by the geometric series test. And to find the exact value, obviously we're going to use the same formula, so a sub 1 over 1 minus r. A sub 1, obviously I just plug in 1 for n, so that will be equal to negative 1/3 times negative 3/4 to the first power. So we'll have negative 1/3 times negative 3/4, which is going to be equal to 3/12, and simplified down to 1/4. So we'll have 1/4, which is our a1, over 1 minus r, and obviously our r is negative 3/4, don't forget the negative. Minus a negative is plus a positive, so 1 plus 3/4. 1 plus 3/4 is going to be 4 over 4 plus 3 over 4, so 7 over 4. And dividing by 7 over 4 is the same thing as multiplying by 4 over 7. So the 4's will cancel, and our final answer is the series will converge to the value of 1 over 7. So let's take a look at the telescoping series. Now recall that this series, the telescoping, along with the geometric series, are the only two series tests where you can actually find the real sum of the series. So let's take a look at number 1 now. The series from 1 to infinity of 1 over n plus 1 minus 1 over n plus 3. Now whenever you have two fractions being added or subtracted to each other, and you have linear factors, n plus 1 and n plus 3, like so. This is probably a good indicator that this is a telescoping series. And this is a relatively easy test because the only way to find out whether a telescoping series will converge or diverge is by plugging in numbers. So remember that a series is basically taking a sequence like a sub n and adding each term in the sequence. So we have a sub 1 plus a sub 2 plus a sub 3 and so forth. So if these two fractions combined, if that is our a sub n, then we're just going to take the first term when we plug in 1 for n, plus the second term, plus the third term, and so forth. And you'll end up realizing that there's a pattern. So let's just start off by plugging in 1, since that's our bottom bound, for n. So if I do so, we'll get 1 over 1 plus 1, which is 2, minus 1 over 1 plus 3, which is 4. So that is our a sub 1 value. That is our first term in the sequence. So now plus, now a sub 2. So when I plug in 2 for n into this sequence, we'll get 1 over 3 minus 1 over 2 plus 3, which is 5. Plus now our third term. When I plug in 3, I'll get 1 over 3 plus 1, which is 4, minus 1 over 3 plus 3, which is 6. And let's just plug in one more term, a sub 4. When I plug in 4 for n, we'll get 1 over 1 plus 4, which is 5, minus 1 over 4 plus 3, which is 7. And actually, let's just do one more just in case. A sub 5, the fifth term in the sequence. When we add it, we'll get 1 over 5 plus 1, which is 6, minus 1 over 5 plus 3, which is 8. So notice how you can actually see a pattern here, where negative 1/4 and positive 1/4, they'll cancel. Negative 1/5, positive 1/5, they'll cancel. Negative 1/6, positive 1/6, they'll cancel. And if we continue to go, negative 1 7, negative 1 over 7, and a positive 1 over 7 will also cancel. And negative 1 over 8 will also cancel. And this will leave us with only two terms left, a 1/2, positive 1/2, and a positive 1/3. So the real sum of this telescoping series is truly going to be 1/2 plus 1/3. If I were to have common denominators, just change it to 3 over 6 plus 2 over 6. And this series will converge to the value of 5 over 6. Now keep in mind that a telescoping series will converge if you get any finite answer or finite number, and it will diverge also if you get does not exist or plus or minus infinity. And keep in mind that a telescoping series can diverge, even though it's not that common, and it will only diverge if you get something like does not exist or you get plus or minus infinity. So now on to number 2. We have the series from 2 to infinity of 2 over n squared minus 1. Now believe it or not, this is actually a telescoping series because we have to first change the series. So if we break 2 over n squared minus 1 and we break the denominator n squared minus 1 into two linear factors, we'll get 2 over n plus 1 times n minus 1. And now notice how we have two linear factors on the denominator, so we can use partial fraction decomposition to break it into two smaller fractions. So once again, to review partial fraction, we're going to set this equal to a constant a over the first factor plus another constant b over the second factor, n minus 1. So if I were to bring this equation down a little bit, what I'm going to do now is multiply both sides by these two factors. We get n plus 1 times n minus 1. And this side also by the two linear factors. So notice how they will cancel on the left side. So we'll get 2 equals, and then I can distribute these factors into both terms. So we'll get a over n plus 1 times n plus 1 times n minus 1 plus b over n minus 1 times n plus 1 times n minus 1. Notice the n plus 1s will cancel on the a side, and then on the b side the n minus 1s will cancel. So simplifying this, we'll get 2 equals a times n minus 1 plus b times n plus 1. So now all I have to do is plug in a number for n that will cancel out one term and solve for the other term. So let's say I plug in first 1 for n. When I do so, I'll get 2 equals a times 1 minus 1, which is 0, plus b times 2, or 1 plus 1, which is 2. So we'll get 2 equals 2 times b, since a times 0 is just 0, which means that b is going to be equal to 2 over 2, which is 1. So now instead of 1, let's plug in negative 1 for n. When I do that, I'll get 2 equals negative 1 times 1, negative 1 minus 1, which is negative 2 times a, plus b times negative 1 plus 1, which is 0. Obviously that's just 0, so we're left with 2 equals negative 2a, which means a is going to equal negative 2 over 2, which is negative 1. So now I can go back up to the partial fraction here, where a over n plus 1 plus b over n minus 1, and I can substitute my values in. So we'll get negative 1 over n plus 1 plus b, which is equal to 1, so 1 over n minus 1. Now I'm just going to rearrange these two and then put the negative out front. So we'll get the series. Once again, the series is from 2 to infinity of 2 over n minus 1, but we have broken down that fraction into 2 smaller fractions, like so. So we have the series from n equals 2 to infinity of 1 over n minus 1 minus 1 over n plus 1. So now that we have it broken down, we can now plug in values and test the telescoping series. So obviously 2 is our bottom bound, so I'm going to first plug in 2 for n. So when we do so, we'll get 1 over 2 minus 1, which is 1, minus 1 over 2 plus 1, which is 3. So that is our a sub 1, or our first term. Once again, a series is adding terms in a sequence, so we're going to plus the next term, a sub 2. Or this time, instead of 2, I'm going to plug in the next number up, so I'll plug in 3. So when I plug in 3, we'll get 1 over 3 minus 1, which is 2, minus 1 over 3 plus 1, which is 4. So now let's plug in 4. Let's plug in 4. So we get 1 over 4 minus 1, which is 3, minus 1 over 4 plus 1, which is 5. Let's plug in one more term. When I plug in 5, I'll get 1 over 5 minus 1, which is 4, minus 1 over 5 plus 1, which is 6. So notice how the negative 1/3 and the 1/3 cancel, and the negative 1/4 and the 1/4 will also cancel. And as we plug in more numbers, the negative 1/5 will cancel and the negative 1/6 will cancel as well. So all we're left with are the 1 and the 1/2. So the sum of this telescoping series is going to be equal to 1 over 1, which is 1, plus 1/2, or 3/2.